Today, I am delighted to share not just one speaker, but four from our community that will be showing how to apply methods from complexity science on a variety of topics, ranging from gender equity to customer preferences to creation of celestial bodies, as well as how the wisdom of crowds can impact decision making during destructive events. Please hold your questions until the end and do wait for the microphone. That way our participants who are joining us live online, hello everybody online, can also hear the questions. And if you are online, please put your questions in the chat and we will get to those at the end of the talk. Without further ado, it is my distinct pleasure to welcome our colleague, Tara Saurirajan, who will be sharing with us, research assistant professor working with Professor Brian Utsi, and she will be sharing with us her research on gender equity and pushing boundaries in innovation. So thank you and welcome, Tara.
Thanks so much, Alana. Hi, everybody. So today I'm going to be talking to you about the glass ceiling in boundary pushing innovation. So what is the status quo of gender in innovation? Everyone is likely familiar with the gender gap in STEM. And a gender gap leads to gender inequalities, not only in terms of work opportunities, salaries, and educational choices, but the idea that society fails to pull from a vast pool of perspectives to solve its most pressing problems. When women became more common in the labor force, they unfortunately encountered a glass ceiling in the form of barriers to their promotion in leadership positions. Now, we want to look at gender inequality specifically in the context of innovation. And one way to measure innovation is through patenting. Patenting is a huge industry globally, and if you just ignore the hundreds of billions of dollars of R&D associated with innovation, patents alone in the US every year comprise a $40 billion industry. So we want to look at specifically how gender inequalities manifest in different barriers to female success in innovation and patenting. So looking at different kinds of innovation, the majority of innovation we classify as day-to-day work, which consists of incremental step-by-step advances, and it comprises the majority of innovation. However, there's a subset of research that we call blue sky work. And this is work that is novel, unusual, and makes atypical combinations of pre-existing knowledge to create something new. The gender gaps in creative work are exacerbated by existing gender imbalances in STEM, but it would also imply that women face an innovation glass ceiling. It leads us to ask the following question: can all researchers be path breakers, regardless of their gender? Can they reach for that blue sky innovation? So we study this in the context of patent applications, like I mentioned, on an international set of data. First, data from the US Patent Office, as well as data from UK and Canada. To focus in on our largest data set from the US, we have around 6 million patent applications, each associated with a status, accepted or abandoned. This is from around the last 20 years, and we have a variety of attributes. For example, the inventors who are making these inventions, we have their genders as inferred from a gender detection algorithm, as well as team size, their experience, whether or not they're coming from a large company or entity. And we have similar characteristics about the examiners that are evaluating these patent applications. Something interesting about patents is that they have been classified by the technological fields that they're comprised, and these are called CPC codes, and it's important to note this so we can control for different variation between different scientific fields. And we also measure impact in a variety of ways, from citation counts through this idea of maintenance fees, because important valuable patents need to pay a fee to be maintained. So this is another way to measure impact. Now that I've talked to you a little bit about the data, let's talk a little bit about the methods we use. We want to construct a measure that allows us to estimate just how atypical, non-obvious, and boundary-spanning the technical areas combined in a particular patent are. So let me present this simple example of two inventions denoted in the pink bubbles: the old thermostat on the bottom and the Google Nest, which we'll call the new thermostat up top. So the old thermostat combines two CPC codes, or these fields: air conditioning and temperature control. These are incremental changes. However, let's consider a new type of thermostat, the Google Nest. The Google Nest allows a user to remotely set the temperature with a smartphone. It adds this third field regarding digital information transmission. And this field has been rarely combined with the more traditional thermostat related fields. It shows that the Google Nest represents a boundary spanning invention and is more of a divergence from previous technology, as we can see this atypical link to digital information transmission denoted with that red arrow. We leverage an application's tendency to be classified in multiple technical areas to be able to create a measure of how typical or atypical a combination of fields in a patent is. So, how do we represent this mathematically? Let's draw our attention to the gray figure on the top. Here I denote a co-occurrence network of topics. Each of these topics are these technical fields, as I represent these nodes A, B, C, D, etc. The links between them represent how often they co-occur on patents. For example, A and C are heavily combined versus C and D, which are not so heavily combined. A link between nodes A and B would represent something that is an atypical link, versus other links may be more common, conventional, or typical. So talking about the math, how do we construct this metric? It's basically a z-score between two topics or fields, alpha and beta. And this measure shows us the difference between the observed number of co-occurrences of two fields and the expected number of co-occurrences of those fields. And this expected model is basically a model that randomizes CPC code arrangement while preserving certain features. So now we've represented atypicality of two fields being combined, but we want a measure that represents the atypicality at the level of a particular application. So what can we do? We have a z-score for two pairs of fields, but we can compute this measure for all pairs of fields and get something like the heat map on the right, where we show atypicality of two fields being combined. What we then do is we take all the fields in a particular patent application and take the minimum dyadic distance as representative of the most atypical, most boundary spanning link. So now we've covered a little bit about the data and the measures we're using. So let's talk about some results. We find that women inventors have poorer outcomes across several different ways of measuring success in innovation. If you draw your attention to the top left figure, here we denote success by first author inventor gender. We see that male and unknown gender inventors have higher success rates than female inventors, suggesting that there might be gender bias through first name gender stereotyping. If you draw your attention to the top right figure, here we see that there are persisting lower success rates for female inventor teams as compared to male teams. As we show in red, the difference between female and male teams, and females are always lower, as this line is always below 0. If you draw your attention now to the bottom left figure, here's an important, interesting feature of patents. Each patent application comes in with a number of claims saying, hey, my invention does this, 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 etc. And a patent examiner can come and evaluate and reject a certain number of these claims or edit them. So here we measure for a certain number of initial claims on the x-axis, how much are these patent application claims shrunk by examiners? What we find is that female teams are shrunk more across the board than male teams. And lastly, in the bottom right figure, we see that female teams take longer for their patent applications to be successfully granted than male teams, showing overall that females have poorer outcomes, different ways of measuring success. So what happens now if we predict patent status or patent acceptance? So what we find is that there is a female gender penalty for both female inventors and examiners. We also see that creativity, or how atypical an invention is, has a positive effect on the likelihood of that patent being accepted, which is something we would expect. Most interestingly, the interaction between gender and atypicality is not only significant, but it is negative, which I'll touch on what that looks like shortly. Our models have a lot of controls, such as controls for year, team size, field level variation, as well as experience, and whether or not an application is coming from a large company. And we still see that despite all of this, females are penalized, but they are penalized especially when they do creative, boundary pushing work. So now let's talk about the interaction between gender and atypicality or creativity. If you draw your attention to the center figure, the x-axis represents atypicality. The further right we go, the more atypical or boundary pushing an invention is. The further left, the more conventional it is. And then we see female teams denoted by by red lines. And the more dark red the line is, the more females. So we see 100% females here, going all the way to 0% female or 100% male with the lightest line. So let's look at the 100% female team. When they do more boundary pushing work, their likelihood of the patent being accepted goes down. However, when males do boundary pushing work, the other line, that slope literally flips. They are heavily rewarded for doing boundary pushing work. Our findings suggest a mechanism for how some of the gender bias in patenting manifests. When examiners encounter inventions that are difficult to fit into existing mental models because they combine these rarely combined technical areas and technologies, it's easier for them to rely on different kinds of correlates for success like gender or other demographic features. You could say, hey, maybe women just don't negotiate enough for their patent to be successful. They don't ask, quote unquote. So we actually have very interesting data that categorizes the nature of interactions between inventors and examiners evaluating them by gender. And we find wherever an inventor is responding to an examiner in this patent process, there are no statistical differences in how different genders navigate patent prosecution. This rules out some possible explanations for gender imbalances in grant rates. To sum up, we've seen that gender inequality still persists in innovation today. Why is this important? Creative work has the highest potential for the most outsized impact. This can be measured through a variety of ways, through citations, through economic impact, and through the influence on the future of innovation. The gender gap is pervasive, but it's especially salient when women make these boundary-spanning technological contributions. Fewer creative inventions get granted, and it upsets the incentive system not only of patent law, but of innovation in general. This work leads to this uncovering of this innovation glass ceiling and reveals its possible mechanisms to better combat gender inequality in the system, for example, through education or inventor blind examination. Lastly, we have evidence that this is a global phenomena through our analysis of the UK and Canada patent system. And it shows that this is a global problem that has a pressing need to be solved. Thank you so much, and I'll take any questions over email or at the end. Thank you.
Thank you, Tara. Great presentation as always. It is my pleasure to introduce our next speaker, Ruoming Gong, who will be talking with us. He works with Professor Danny Abrams, and he will be talking about planetary ring formation. Please join me in welcoming Ruoming.
Hi everyone. So today I'm going to introduce a new idea on planetary ring formation based on a collision model and a coupled oscillator model. So many of you may heard that the formation of the moon is formed during the collision between the Earth and another small planet. After the collision, the debris of the planet revolving around the Earth and finally becomes the moon we see today. However, there's a gap here. So why does the debris form the moon instead of remaining as small particles revolving around the Earth? So in general, the moon of the planet forms from this so-called accretion disk as shown in the figures. So the accretion disk is formed by small pieces of rock and ice. And it could be from the debris of the planet, or it could be from other small bodies trapped by the gravity of the central planet. So the question is, how did the moon form from this accretion disk? So we have several observations from our solar system, which can be categorized into two cases. So for the giant gas planets like Saturn and Jupiter, they have rings. as we see from the left figures. So Saturn has so far the largest rings in the solar system, and we can even see it from Earth. And on the other hand, we have the small planets like the Earth and the Mars. They don't have rings, but only have moons. So why? So when do we have moons and when do we have rings? To answer this question, we consider the simple toy model, which only involves the collisions. So here's our collision model. We assume that the particle is revolving around the circular orbits. I should mention that in general, the particles should revolving around the elliptical orbit. But here, to make our model as simple as possible, we assume the orbits is all circular. And we know that the particles on different orbits have different angular speed. So if the two orbits are close enough to each other, it is possible for the particles to collide with each other, as we see from the right figures. If the collision happens, it will result in a particle moving into the new orbits. We made several assumptions about the collision here. So we assume the angular momentum and the mass is preserved before and after collision. There could be an energy loss due to the deformation of small bodies and the heat transfer. Actually, in our simulation, we impose a random energy loss at each collisions. So after the collision, there are three possible outcomes. So here, chi is the coefficient of restitution. So when chi is equal to 0, that means we have elastic collision, which means there's no energy loss. And the particles will exchange their orbit after the collision, as we see from the left figure. And when chi is equal to 1, we have perfect inelastic collision, and the two particles will end up in the same orbits. And when chi is between 0 and 1, the particles will move into new orbits, which is between the old orbits. So we conclude here, as showed here, if the particles, after the collision, the particles will move closer to each other if there's an energy loss. Oh, so before we move to next slide, so for this collision model, it is actually analytically untractable. If you consider if you have millions or billions of particles, it is hard to track the positions of each particles after a large amount of collisions. So we need another model where we treat the particles as coupled oscillators. So this model is known as the Kuromoto model on networks, which is given in equation 1. So here, theta I is the phase of the particle. Wi is the angular speed of which only depends on the radius of the radius of the orbit, and k is the coefficient. K is the coupling strength, which reflects the strength of the collision, and n is number of particles. Dij provides the network structure, and f is the interaction function, captures the effect of collision. So in animation, I showed two typical behavior of this model. So I start with the fully connected network, and the interaction function I choose is the sine interaction function. And on the left side, I choose the small coupling strength k, and we see it remain as the rings. And on the right side, I choose large coupling strength k, and we see the particles synchronize, and it looks like a moon in the end. So the advantage of this coupled oscillator model is that it is easier to analyze analytically. So now the task is, how do we link the collision model with this coupled oscillator model? Let's back to equation 1. There are three things left to be determined. The coupling strength K, the network structure, and the interaction function F. So in the next slides, I'm going to link the coupling strength K with the parameters in the collision model. So there are three important parameters for the initial conditions of the collision model. So D is the effective particle size, which is the radius of this small yellow disk. And sigma R is the width of the distribution of the particles. And N is the number of particles. So we have a 2D argument for the coupling strength K. So K is proportional to the inverse of the expected time of collision. And the expected time of collision is proportional to 1 over N times the ratio between the gray area and the yellow area. And the gray area and the yellow area can be computed using the parameters we introduced before. So this argument sounds intuitive, but it does not match the simulation. So actually, in fact, we figure out our collision model is a one-dimension model. So we need to adjust our argument into one dimension. So here's the figures for the one-dimension argument. And now the thickness of the yellow ring is our effective particle size d. And the sigma r as before is the width of the distribution of the particles. And then now we have the expected time of collision is proportional to 1 over n squared times the ratio of sigma r and d. So in the last slides, we discussed the relation between the k and the parameter of the collision model. And here we want to discuss the network structure and how the network structure linked to the parameter of the collision model. So on the left figure, we choose d over sigma r equal to 0.2, and we see it provides a chain-like sparse network. And on the right figure, we choose d over sigma r equal to 1, and we see a very dense, almost fully connected network. So you may notice that both the coupling strength and the network structure depends on the ratio d over sigma r. So that means if you choose a relatively dense network, that also means you are choosing a relatively large coupling strength k. So here's the simulation for the collision model. So we start with 300 particles, and it will end up with a few moons, but we need to be a little bit patient because it takes a while. So to make the simulation faster, we actually make it event-driven instead of time-driven. So that means we made the phase plot after after each collision. So let's wait a little bit. Oh, it's never ending. So it ends up with 4 moons, and we will see the time to see that happen is relatively long. And so here we provide 2 typical results of the simulation. So when we choose d over sigma r equal to 0.2, we see it remains as the rings. And when we have d over sigma r equal to 1, and we see it end up with several moons. So to compare the collision model and the coupled oscillator model, we also plot the order of synchronization with the d over sigma r changed. So the order of synchronization is between 0 and 1. When it's close to 0, that means we have the rings. And when it is equal to 1, that means we have the single moons. So we observe that for both models, we have a phase transition. And the phase transition matches each other. And another thing I want to mention here is that the phase transition is not very sharp here. The reason for that is because when we change d over sigma r, we are changing the coupling strength and the network structure at the same time. So what is the takeaway from this work? So the first point is the collisions of the particles can produce rings and moons. And whether we get rings and moons in the end depends on the mass and the size of the central body, because d and sigma r depends on those. And another observation is that the simple oscillator models shows a similar phase transition as the collision models. So this may imply that we can use the coupled oscillator models to study the formation of the rings and moons. So this is a story, and thank you for listening. I'm happy to answer any questions.
Thanks, Roming. And we will take questions at the end. Now I would like to introduce Yaochen Tui, who works with Professor Wei Chen, and will be talking about network-based customer preference models. Thank you.
So hello everyone, my name is Yaxin. I'm from Northwestern University in Mechanical Engineering Department. I'm currently pursuing my PhD degree. Today, I would like to present a collaborative research on network-based customer preference modeling. In my presentation, I will first introduce the customer preference and network-based models and introduce the data source we are using. And then I will use 2 case studies to illustrate the ways that we modeling customer preference at 2 different levels. First, let's take a look at how customer preference is affected in a complex social technical system. Let's use an example of the electric vehicle market. There are many different customers, may have very different backgrounds and demographic attributes. And when they considering to purchase the electric vehicle, they may first consider several car models that meets their needs and then choose one model out of their consideration set. And in this process, the design engineers, they need to design how to meet customer needs, and from the mechanical point of view, such as they need to do the battery design and engine design, and there's lots of trade-offs in the design process, like the cost and the best performance. However, it is not always the case to design the top performance top performance cars, because you need to take the competitors into consideration. You need to figure out your market positioning. And what makes this process more complex is there's social influence among customers. Like the green attitudes can influence from your family or friends can influence your choice on the electric vehicles. And government also play an important role here. They can by making policies and incentives to influence your decision-making process. So in this talk, we would like to focus on how to understand the customer preference in such a complex social technical system, and especially focus on how to build the network model to model this complex system. And in the previous work, a multidimensional network-based customer product network has been proposed. And in this network, there are 2 types of nodes characterized by the customers and products. Customer nodes are in red and nodes are in blue. And there are a relationship between customers, which are their social interactions. And in the product layer, they have the computation between products as well as preference association between products. And within those customer and product layer, between the customer and product layer, there are customers' consideration behavior and customers' choice behavior. And the goal is to, by using this complex social technical system, we can understand or analyze the dependency of the customer and product relationship. So before we dive into the method session, let's take a look at what the data source we are using here. The data set we're using is called New Car Buyer Survey data from the Chinese market. And in this data set, we have around 50,000 respondents each year and 400 vehicles. And customers will give us their considered and purchased cars in the survey data. For example, Joy may consider 3 cars and choose Honda CR-V in the end. And Megan choose Ford Escape over the other 2 considerations. And Lee choose Kia Niro over the other Toyota RAV4. Besides those information, we also have the information like vehicle attributes, customer demographic attributes, usage context, and the perceived vehicle attributes. And within this network model, within the multidimensional network model, there are different level of networks model we can build based on the complexity. The first type of network is unidimensional network, where we only have the product nodes. And the relationship between the products can depict the product computation relationship, which I will talk in the first case study. And in the second case, we have the customer's consideration and the choice in a bipartite network. Those data are reported from the customer in the survey. They reported what car they have considered and purchased. And I will illustrate this in the second case study. And more complex, as we said, we can add the customer social relation and product computation relation. But in this case, the customer social relation can be added either from the real data, like if the customer specify who they have connected with, but that's only in the case we have sufficient data. But in the other case, we may simulate the customer social network based on their similarity that was done in the previous work. Now I will talk about the two case studies used in this presentation. The first study talk about the car computation relationship using a unit dimension network, and one model called valued exponential random graph model have been applied in this case study. And in the second case study, we investigate the customer two-stage decision-making process by looking at a bipartite network and using bipartite ergon. So in the first case study, we are looking for the unit dimensional car computation relation. And as we said before, there are two steps in customer making decision, consideration and choice. And correspondingly, there are two types of networks we can build on. The first is co-consideration network, and the second is choice network. So in the co-consideration network, the two cars are being linked if they are co-considered by some customers, and the strength of link denotes how many customers are consider them together. And in the choice network, the links denotes if two customers are consider them together, while some customers choose one car over the other. In this example, there are 25 plus 6 customers consider Buick Enclave and Ford Edge together, while 25 out of them choose Buick Enclave over Ford Edge. That is how we define this network. And by establishing such a network, we investigate the customer preference in an aggregated choice behavior, and we can use this type of computation network to study the market behind the car design. And by building the co-consideration and choice network, our first research question is, how can we understand and predict the computation relationship between products using network analysis? So the network model we are using here is called exponential random graph model. The exponential random graph model is short for ergon. Basically, it measures the possibility of the network structure and expresses it as a exponential form of coefficients multiplies input variables. And the input variables here can include some node attributes, edge attributes, as well as network structure effects. And by estimating the unknown coefficients, we can estimate the effects of all the input variables. However, this ergon model is designed for binary case, like the link strength is just binary. In our case, because we want to capture how strong the computation are they, so we use the valued ergon, which is recently developed to capture the link strength. And besides the link strength we have defined in the previous slides, there is another thing we need to determine. It's called the reference distribution. Is HY in this form, and the reference distribution reflects the sample space and the baseline distribution of the link strengths, which should reflect our prior knowledge of our data set. And this is a kind of a partial of the results of our estimated coefficients in the co-consideration network. As I said, we have different type of input variables. The network structure effects, which measures market effects. And the main effects, what we have here is price, fuel consumption, and brand origin, where the car come from. And some homophily effects like the market segment matching, brand origin matching, and the price difference. They are measured a similarity or difference between a pair of nodes. And some key findings here, if you just use an example, like the brand origin from American is positive and it's 0.29 and significant, which we can calculate the odds ratio is 1.33. So that indicates that compared to the reference group, which is Chinese brand, the brand origin from American can actually has a higher chance to be co-considered by the customers. And we also noticed that the homophily effects, which measure similarities, they are significant and very important in our results, which verifies our common belief that the customer tends to consider cars with similar features. And the next step, we use this valued ergon to use the current year network to predict the future network when the model design change or there's new car models involved into the market. As an example of the real market evolution, we can see from 2013 to 2014, the Great Wall Hoover has gained much more co-considerations with other cars. And by using the estimated coefficients from 2013, we actually can show that the trained model predicts link strength of future unseen data reasonably well. And in our second case study, we studied the customer two-stage decision-making process, consideration network and choice network, where we have both customer nodes and car nodes. And in the consideration network, each customer connects to 2 to 3 cars, and in the choice network, each customer only connects to 1 car. And we want to investigate how can we understand the difference in customer consideration and choice behavior. There is one thing which is unique in this model is the choice making stage is actually conditional on the first consideration set formation stage, because the customer's choice should only be based on the customer consideration. And there are several settings we need to work on that. First, we need to work on the conditional relationship. Basically, we use the customer consideration information as an offset matrix and make sure that the link is only formed between customer and their choice set. And also another constraint is that we enforce the customer in the second stage can only form 1 link to the cars because they can only choose 1 cars. And by setting those constraints, we are able to mimic the real customer choice behavior based on their consideration. And here is, again, like partial results of our consideration stage and choice stage. We also have different type of input variables, car attributes, customer attributes, and network effects. What I want to show here is first the market distribution effects, which we basically measured based on the geometrically weighted degree distribution. And the negative effects shows that the market distribution is more skewed, like some cars are more popular than the others. And we do notice some difference between customer consideration and the choices, like the impact are different in 2 stages, such as this overall satisfaction coefficient is not important in the consideration stage, but it's more important in the purchase stage. And then come to the key takeaways and next steps. In my presentation, we show that by using the network-based model, we are able to understand customer preference in social technical systems, and the ergon model help us to understand and predict the future market. In our next step, we want to incorporate the social influence and product association links in the customer layer and product layer. And thank you so much, and those are all my collaborators.
Thanks so much, Yaoxin. Next, it is my pleasure to introduce Elisa Borowski, who works with Amanda Stathopoulos and Agnes Horvat. Welcome to you both. And she'll be sharing her work on wisdom of the crowds in multi-hazard events. Thank you so much.
Thank you, Alana, and thank you for Andy for having me here today, and thank you everyone for being here. I'm going to be talking about the role of the crowd in multi-hazard events and decision making. So this is work that I've been able to do under the Center for Engineering, Sustainability, and Resilience grant, which was awarded to Professor Stathopoulos, who is my advisor, and Professor Horvat. So the main thing that I'll be focusing on today, and maybe the only thing for the sake of time, is the flood evacuation that occurs during the COVID-19 pandemic. So for this, the literature shows that for flood evacuations, the role of social capital is significant and positive. People tend to look to their family and friends to see what they're doing during an evacuation and tend to do the same. And we think of crowds generally in this context as being a good thing. They represent social capital, access to resources, human connection and support. But during the COVID-19 pandemic, and this study was done within the first couple months of the pandemic here in the US, we saw that we really didn't know very much about the pandemic. There was a lot of uncertainty. There were no vaccines at that time. The death toll rates were climbing every day. And the crowd started to represent something dangerous and scary and something that we were supposed to avoid. So we wanted to study this context, this overlap of the crowd being something helpful in an evacuation, but harmful, potentially harmful in a pandemic. If there's time at the end, We're also starting some new work on food insecurity during the pandemic, and that's looking at using a crowdsourced platform to deliver food to individuals in need. In this case, in the early stages of the pandemic, there were food shortages due to supply chain challenges and hoarding behavior, and so the crowd represented like competition for resources, but also potentially a way to access resources. So this survey that we did was based on an event that happened in Michigan in May 2020. And what happened were two dams failed, and there was a flood, and over 11,000 individuals had to evacuate during the pandemic lockdown. So we designed a survey, and we launched this at the end of June 2020 to about 600 respondents in 6 different states. And I'm excited that I'm not the first person to present on choice sets today, or choice experiments. But so here we gave a hypothetical scenario where we said you have to evacuate within 2 hours, and you don't have a personal vehicle. How will you choose to evacuate? And so we presented respondents with a series of 9 of these scenarios, showing 3 different rides that they could choose from, or the option to stay behind. Some of the unique features of this were the crowding feature. So in some cases, this was a private vehicle, so that might be like a zip car situation where you're the only person in the car, but it's still a shared car. Or maybe there's a driver, like more like Uber, and you might be sitting in the front seat or the back seat. And then also we said among your 5 closest peers, if presented with this choice situation, here's what percentage of them would choose each of these options. And we also varied the flood threat level so we could see what effect that had. So we took this data and we used a random parameter logit model to estimate this in both preference space, which is typical for our field, and then also willingness to pay space, which gave us some units of dollars so we can compare our coefficients. So some findings that we saw, I'm going to focus mostly on the peer influence findings. We saw that when we consider the choice of whether to stay or go in this flood evacuation, peer influence had a positive effect. And so people were likely to be influenced to do the same thing as what their peers were selecting to do. But as the flood threat level increased, and these values are additive, we can see that that starts to compress down to around 0 or even negative effect. Now, if we look at the decision to evacuate and we look how respondents selected between those 3 different ride options, we see the opposite effect. So there's a negative effect of peer influence on selecting a ride. So if most of your friends were selecting ride 3, for example, you might be more likely to select ride 1 or 2. And this kind of goes against what we're typically thinking about in terms of following the crowd in an evacuation. And this could be related to wanting to diversify a strategy. Once you've decided you're going to step out of your house, you kind of still want to stay away from other people in this multi-hazard scenario. And again, we see as the flood threat level increases, this kind of compresses down to 0. So when things are really extreme, people aren't really looking to see what their friends are doing. They're just sort of doing what they feel they need to do. And then the final finding, we looked at some different ways of perceiving this multi-hazard event. So we asked what kind of perception of risk to your own health you viewed the pandemic, as well as some different emotional effects. So individuals who viewed the pandemic as being a major risk to their health were very likely to stay, which makes a lot of sense. When we presented the scenario of the flood event that happened in Michigan, we asked how likely respondents would be to feel 4 different emotions. So angry, sad, anxious, or afraid. And anxiety and fear came out significant, but they have opposite signs, which is interesting. So if respondents were more likely to feel anxious, they were also more likely to stay, so kind of a freeze response. And if they're more likely to feel fear, they're more likely to evacuate, so maybe a flee response. And there's also an interaction effect, looking at among those who viewed the pandemic as a major threat to their health. As the flood threat level increased, they became less likely to stay. So summarizing the conclusions for that part of the study, and I think I will have time to do the next part. So we found that people tend to follow the crowd when deciding whether or not to evacuate, but go against the crowd when deciding how to evacuate. and the magnitude of the social influence was inversely proportional with the flood threat level. And for more information on this, we have a paper that's currently in press, and there's a preprint available online if you'd like to read that. So looking at the case of pandemic and food insecurity, this is something I'm doing in collaboration with my colleague Gretchen Bella and also a nonprofit organization in Houston, Texas called Crowdsource Rescue. And this is looking at, we have data for the first 2 years of the pandemic, and this is an online platform that people can go to request a need for food to be delivered to them or to volunteer that they were willing to deliver food. And one of the first ways that we've looked at this data is using the adoption of innovation theory. And so we divided up all of the help requests that we have into these different categories and looked at how likely each household would be to fall into, whether it's the first 2.5% of adopters, so the innovators, or the next 13.5%, and so on. And something interesting that we found here, focusing more on the last households to adopt, we see that they tend to be among the lowest income in an already low income sample. So the highest income in the sample is about 15,000. So they have smaller household sizes, fewer adults, less likely to be enrolled in different financial assistance programs or food assistance programs, had more children in the household, and might have been residing in a shelter at that time. So we think that this is really highlighting households that were somewhat isolated and disconnected from other social resources. So while this crowdsourcing service is really designed to help those most in need, it might not be reaching the households that need it the most. And so some future work that we're going to do is look at different multi-hazard events that occurred during the first 2 years of the pandemic, so like Hurricane Laura and the winter storm in 2021. So just some final takeaways. When we ask what is the wisdom of the crowd and multi-hazard event, we see it is mixed as we expect. There are benefits, access to material resources, to information, and to different advice and strategies, whether that's explicitly or implicitly. And there are also risks, so viral contagion, traffic congestion, and strain on resources. With that, thank you for your time.
Thanks, Elisa. And maybe I can invite all of our speakers to come up to the front and we can ask questions. Andy will be passing around the mic.
I will kick things off with a question from the online audience for Tara. Hold on a second. This is from Neil Ormos. He has a multi-part question. He asks, patent classification systems are arbitrary. Have you considered the results from US or international classification systems instead of CPC? Have you explored bias in legal representation? Most patent applications don't prosecute applications per se, but are represented by a patent attorney who might be the operative source of bias. And then lastly, he asks, have you explored cultural bias against women among examiners by inference from inventor surnames? So I know that was a lot of questions there.
Could you just like repeat the last 3 words? Cultural bias?
Oh, have you explored cultural bias against women among examiners, e.g. by inference from inventor surnames?
Oh, I see. Okay, let me just think. So the first part I think was about CPC codes. I don't really understand what's arbitrary about them. Like it's like a classification system with different levels of hierarchy. From like a really broad field level, sort of this is like chemistry or metallurgy, to something very specific. And this sort of methodology to represent how atypical an innovation is using the CPC networks, co-occurrence and expected co-occurrence, has been validated and published before. But we do also look at international data from the Canada and the UK, which use similar classification systems, and find that these findings, like the atypicality results, hold in international patent data as well. Sorry, Andy, what was the second part of that question?
have you?
Patent lawyers, yes, thank you. So, yes, we did look at patent lawyers and the genders, and we don't find that patent lawyers have a significant, their gender has like a significant effect in predicting patentability or future impact. We do look at patent lawyers instead of just inventors in terms of how they interact with the patent examiners, and we still don't find gender differences in how the gender of different attorneys matters in how they navigate those back and forths with examiners. And lastly, no, we do not look at last name like race inference, but we do look at whether or not these inventors are coming domestic from the U.S. or international as a control in some of our models as well. Thanks for the question, Andy.
He actually has another question, but I will email that to you so we can move on to some other questions. Are there any questions from people in the room?
I don't mean to hog the stage, but I've got two questions for two of you. So I'll ask them that way you can think about them. So Tara, I noticed that on one of your graphs, it was inversely proportional between incremental patents and really real changing patents. Whereas it was clear that the female patent submittal people were in trouble when it was very innovative. It seemed like they had an advantage when it was incremental, and that seemed surprising. I want to ask you about that. And then Alyssa, I want to comment that you mentioned something very interesting, that fear and anxiety had opposite effects. I'm wondering whether you are digging deeper into that, because it's a subtle distinction, but very important in the way you communicate and address potential needs.
So yeah, that's a great point. Actually, if you look closely on that graph, so that part was in the deeply conventional part of those patents, like that whole section. And actually, all of those confidence intervals are overlapping as we get more to the deeply conventional. So it's kind of like that. There's not actually much gender difference when it's deeply conventional.
Thanks for your question. Also, it's a really good question. I don't have plans to look into it deeper, but I think it really should. And I do agree that it's very interesting. It's something that we're really thinking about in terms of how communication is done around emergency events. I think fear tends to be when there is one specific thing happening that you're afraid of, and anxiety is when you're just sort of overloaded with information. And I think a lot of that was happening during this multi-hazard event. So that might suggest, really focusing, having more clear and focused communication around what needs to be done. It's hard to say, saying that in retrospect, we really didn't know at that time what we should be doing. So, but I think it's a really interesting area of exploration, and I hope that it continues going forward.
I want to compliment all the speakers. This was such a fun session. And then a question for Tara. You have this unique view on also the examiner side, including gender information. And you have this result that seems to suggest that female examiners are also disadvantaged. Can you expand a little bit on that? What do you make of that? And then in terms of interventions, do you have any ideas? You mentioned some interventions for the inventor side. I think those are cool, in particular the one where we conceal names. But what can we do when it comes to examiner?
Yeah, that's a great point, Agnes. Thank you so much for bringing it up. So, yes, we do see a penalty when female examiners are involved, like when there's a female examiner as to male. So, one idea that we kind of had behind that is this like theory called the queen bee effect, if you're familiar with it. Basically, where like females in positions of power sort of like penalize more. And it's kind of just more of a theory at this point. We do see some evidence to suggest that female examiners are a little stricter, even when controlling for their experience level of the examiners, measured through a lot of ways. And it would definitely be interesting to look into more. As for policy interventions for examiners, I think maybe like one that we thought of is honestly education and informing them of this sort of like phenomena that occurs, because there are a lot of other examiner related phenomena, like examiners who are tenured longer tend to have, they take in a lot more applications more quickly and they reject more. So, I think education of the phenomena could be helpful for female examiners and maybe digging into more of why that is the case.
I just want to know if, in general, there is just one examiner or is it an application is reviewed by multiple.
There's one examiner.
And do you think using that number, say, set of people?
Totally. So we actually have like an interesting subset of data where we look at appealed patents that go through to like a board of examiners. And we still see like similar gender dynamics there, but definitely perhaps multiple examiners could be a way to alleviate some of these gender dynamics.
Yeah, I have a short question for Romy. You built a model and you have two phase, the single moon phase and the ring phase. Have you considered fit the available data set into your model? Like you calculate T and sigma from Earth and the Jupiter, where are they in your model?
Oh, so yes. Sorry. Yeah. Is that working? Yeah, it's working. So that's a good question. So actually, we use the data for the Jupiters for our model. Oh no, actually Saturn's for our model because Saturn has so far like the biggest ring in the solar system, and we also try to use the data for Earth for that for the simulation. But actually, it does not really make a difference because like we can always to rescale our time to like make the when we rescale our time, it also means we rescale our the radius of the radius of the orbits. So I think the most important question is like how the network structure depends on the mass and the size of the planets. And this question is still need to be explored because we don't really understand like how the D and sigma R depends on the size and the mass of the bodies. So far it's just we link the two models, which one is the collision model with the coupled oscillator model. But for each parameters, and we still need to study how the sigma R and the D linked to the mass and the size of the planet. Yeah. Thank you.
I have a question. So first of all, thank you all for exciting talks. These are all amazing. I have a question for Tara. So you look at pattern, and I wonder, you look at the differences in language that people write up in their pattern.
Yeah, that's a great.
Like maybe men are more likely to like exaggerate their potential impact or frame their technology as more positive, broad. So maybe this can explain the underlying differences.
Yeah, that's a great question. Thanks for bringing it up. So, something interesting about patents is that most of the writing is done by the attorneys and not the inventors. And um, also, the language of a patent, from what I've heard from our one of our authors who is in patent law, um, is very precise and specific. So, for example, the number of words in a patent application's claims correlates to the breadth of the invention they're claiming, etc. So we've also kind of studied all of those measures for like the breadth of a patent in terms of the number of claims, the words in like the words on the claims length that have been previously correlated with how I guess like powerful or like how much breadth a patent is claiming. And we still see those gender differences even when we look at those measures. It would be interesting to look at the specific language used as well.
I'm just going to jump in and see if we have any questions for Yaojin, who gave a great presentation. We'd like to make sure everybody has an opportunity to answer a question.
So I have two questions for Yashin. So you work on choice modeling problems, and many of us here come from the field of choice modeling using probabilistic models. So I wonder what role can randomness play in your model? It seems like when you assign the choice to a customer, you do that in a very deterministic way. But if there is uncertainty or hesitation or any kind of randomness, can you build that into your process? That's my question number one. Number two, in your second case study, when you have the consideration then choice process, some of these signs or parameters were contradictory, right? They had a positive sign for consideration, but negative for the choice, and vice versa. How do you use that practically for like design decisions, or how can you make sense of those kind of dual sign context?
Yeah, thank you so much for your questions. So for the first question, I guess it's like randomness in our data set. Because we are like more like a data-driven design, so our data is like from customer directly. That's the reason why we assign customers choice link directly. But like, as a choice modeling, we do capture the randomness by the model, because our model is still a probabilistic model, so it's not a deterministic model. There is still when we do the prediction or estimation, there's still a chance of the link formation. There's a kind of probability associated with it. It's not like either 0 or 1. It's more like it's a continuous variable. And thank you also for the second question. The second question was about like the two difference between consideration stage and the choice stage. That's exactly what we want to see, like whether customers have differences in two-stage modeling. I think that's also in the choice modeling work. You're trying to identify whether customers consider differently in two stages. So the first I want to say is we want to understand how customers make decisions. Is there any difference? Like we probably, from our common sense, we know when customer form consideration set, we may look at some whether this product meet our needs. And in the second stage, we may look at some performance of certain attributes. That's something why like some attributes play different roles in two stages. And in terms of design or for the product, we may need to like, as a product designer, it's important for you to know, like if you want to more you want more into the customer consideration stage, you may need to consider several things. And if you're already considered by customer a lot, but you're not chosen by customer, what you are going to do? I think that's the implication. Thank you so much.
Nice round of applause for all of our speakers today. Wonderful job. Thank you so very much. For those of you who might be inspired by this great presentation, we are almost filled for our winter lightning talks, but I think we have one slot left. So if anybody would like to, please sign up now, let us know. Go on the website and you can figure out how to do that. Next week, we have Penny Neely from, she's an economist with the World Bank and also with Oxford University, who will be talking about climate change policy. Please grab lunch on your way out, and thank you so much once again for our great speakers. Thank you. Another round of applause.